Hi, in this video, I'd like to go over a few things about Chapter 2, which is entitled The Chemistry of Life. We're going to look at some of the basics of some chemistry areas to kind of get us started thinking in terms of chemistry and how it applies to the living organism, how it applies to anatomy and physiology eventually. Just a couple of chemistry terms here. You probably have seen these already somewhere along the way. Nothing real new here, but matter, when we think of matter, that book definition, that classic definition that you've probably seen before: anything that has mass, it occupies space. And of course, we talk about how things exist, how matter exists in three main states, such as a solid, liquid, or gas. You can think of water, for example. And we'll talk a little bit about water as we go through the video. Water, of course, can be a solid in its frozen state. Water in room temperature is, a liquid, and then water can form into a gaseous vapor. And so, and then of course we are looking at chemistry, which is really studying matter in a lot of different ways and how it interacts with other matter. And we'll start very, very simply down to the very smallest part of matter, which is considered to be the atom. And most of you have probably seen this before as well. Just kind of a refresher here. You see a nice little diagram there of an atom where you have electrons that are outside of the nucleus area. The electrons are negatively charged. They are in different kind of electron cloud areas, what the chemists refer to, and they have different shells that they kind of jump back and forth on. And then, of course, inside of that nucleus, that's where you're going to find the protons and neutrons. Make sure you realize that protons do carry a positive charge. Neutrons do not have a charge, so they're referred to as neutral. And so this is kind of a picture of a stable atom. There's no charge associated with this particular setup here, this particular atom. We'll talk about what happens if there is a change in the charge, if you have an addition of electron and that atom becomes more negative, or if you have the loss of electron and then that atom will become more positive. And so we'll talk about that also in this chapter. We're going to look at a few things, and I want to show you a little bit about the periodic table. And of course, this is not really a chemistry class at all. I'm just kind of giving you a few things to kind of help you out along the way as we start building up to cells in our next chapter and understanding a little bit about cell biology. But I think it is important to understand a little bit about the periodic table and things like protons, electrons, the atomic number, different things. And so you probably have seen this before as well. The number of protons in that atom really defines that atom. It defines what that element is. There's your kind of book definition for an element: any substance that cannot be broken down into anything simpler just by any kind of normal chemical means. And so you have an element such as carbon or hydrogen or oxygen, some of these main elements that are part of the human body. And so go back to this again. You have these protons here in that nucleus that carry that positive charge. That really defines which element that you're looking at. And so that's what it says here. The atomic number is going to define that element. And when you look at the periodic table, and this is a very simplified version. If you take a chemistry class, you're going to look at this in a lot more detail. This just kind of gives us a little bit of a simplified version here. There's some information here that we can gather here. But if you look at number 1 right here at the top, this is hydrogen. You see the atomic symbol that's here for that particular element. The 1 up here represents the atomic number, and so that's telling us that there's 1 proton in hydrogen. Now, if you notice, if we change that number, if you change the proton number of protons, you change that atomic number, you change that element. So if we look at this element, it's got 2 protons. This is no longer hydrogen, this is helium. I've changed the number of protons, I've got a new atomic number of 2, and so I have a different element altogether. Right? You add another one, add another proton, you have lithium. You add another proton, you have beryllium. So that's why it says that atomic number, the number of protons, literally is defining that particular element. I mentioned some of these already. These are some of the main elements. There's more, of course, but these are some of the main elements that we're going to be talking about as we get through, especially towards the end of the chapter. We'll look at a little bit of biochemistry, look at those large macro type molecules or biomolecules that make up the human body, things like carbohydrates, lipids, proteins, nucleic acids, all of those types of things. We'll kind of have a quick overview of those towards the end of the chapter. But these are the four main elements that you find in living things in the human body: hydrogen, oxygen. Of course, when you combine these, you have water, hydrogen, two atoms of hydrogen, and then oxygen, H2O. And so, your body is 60 to 70% water. Of course, that varies a little bit, but so you have a large amount of hydrogen and oxygen in the body. You have a large amount of carbon in the body. And so all of those macromolecules that I mentioned, whether it's carbohydrates or lipids or proteins or nucleic acids, all of those have a carbon portion there. And then nitrogen, that's another main element that you'll find in the body. And of course, you've got many different minerals that make up this. It could be things like calcium or magnesium or sodium, even manganese, zinc, and then you have some trace elements that you need just a little bit of, maybe like selenium or copper. You need just a little bit of those elements. So we talked about the atomic number, but you also have what's known as the mass number. So if you were to add up all of the protons and the neutrons in the atom, that would give you the mass number. That's different than the atomic number, because the atomic number is just the number of protons. But if you add up protons and neutrons, you got the mass number. Take a look down here at hydrogen. This is the element hydrogen. The bottom number here represents the atomic number. That tells me that hydrogen has one proton. The top number is the mass number. But notice in our example here, hydrogen has a mass number of 1. And so what that means is that hydrogen does not have any neutrons in the nucleus, right? So if you add up 1 proton and 0 neutrons, I end up with a mass number of 1. And so hydrogen its natural state does not have any neutrons in the nucleus. But notice this over here. It still has the symbol for hydrogen, H. It's got 1 proton, the atomic number, so that means I haven't changed the element. It's still hydrogen, but notice that it has a 2 here for the mass number. So what that tells me is I've got 1 proton in the nucleus, plus I have 1 neutron in the nucleus. Add those together, and I have a mass number of 2. And then we look one more. Look at one more. We've got hydrogen here. It's still hydrogen. I've got 1 proton, but now instead of having 0 or 1 neutrons, I have 2 neutrons in the nucleus. You add up 2 neutrons and 1 proton, you get a total of 3. That's the mass number. What I've done is basically shown you some isotopes. These are atoms with the same atomic number. They've got 1 for each of the atomic numbers here, which means it's the same number of protons, but I have a different mass number because what has changed is the neutrons, right? For hydrogen, what they do is they do change the name here, even though it's technically still hydrogen, but they change the name to let you know that you're dealing with an isotope. Now, sometimes, and many times, isotopes are very unstable. They are trying to get rid of some of that extra energy or extra instability. They're trying to get back into a more stable form. And so what that means is many times they will release some form of energy, usually in the form of some kind of radiation. And so that's called a radioisotope. Section 2, we're going to talk briefly about how matter gets combined, and we'll talk about a few definitions here associated with mixtures and a little bit about bonding. You may have seen this before. There's 3 main types of mixtures we need to look at, and these are applicable to a study of anatomy, because you'll see here in the picture here, we're looking at a suspension, and their example, which is a very good example, is what's inside of your blood. So the suspension here, by definition, is any kind of mixture that has 2 or more substances added together. But notice that The distribution is uneven. In other words, it's not homogeneous, it's not completely dissolved by any means, and that what you have will eventually settle out if you let it sit long enough, right? So think about a vial here or a test tube of blood. You've got different parts of that blood. That's another chapter we'll get into later. But you've got a plasma portion, that's the liquid portion, and then you have a cellular portion that includes your red blood cells, white blood cells, platelets. Those cellular portions will eventually settle down to the bottom. So they'll settle out of that mixture, out of that suspension. You may or may not have seen this word before, a colloid. This is also a mixture where you put two or more things together. In this case, it's very evenly distributed. The particles don't really settle out at this point. And usually those particles, those components are relatively large, well, maybe not large, but they are larger than the next example, which is a solution. Particles still don't settle out. Their example here is milk. Think about what's inside of milk. There's water in milk. There's fat in milk. There's proteins in milk, and they all kind of suspend together in that mixture, which is a colloid. When you go start studying 169, you'll talk about colloid type matrix that's inside of your thyroid gland that suspends and creates a mixture of thyroid hormones, and that's how the thyroid gland kind of stores up those hormones in that colloid type mixture. Last example of a mixture would be a solution. This is probably what you're more familiar with. This is just your everyday example of taking some water, maybe dissolving some sugar in it, or you're making tea or coffee or something. You put some sugar in there, it all dissolves, and that's basically your solution. It's two more substances added together. In this case, they're very small. They do evenly distribute. In this case, also, they don't settle out. They stay in a solution. They stay dissolved, right? So if you take some sugar and you dissolve it in some warm water, it's going to stay dissolved in that solvent. Couple of good words here. The substance that is being dissolved, that's the solute. Okay, so again, if you take that analogy of sugar and water, you dissolve that sugar. The sugar would be the solute. It's being dissolved in a substance called the solvent. And so water in that case would be the solvent. They've got kind of the same type of example. They take a type of sugar, glucose. This is a simple sugar we'll look at later in the chapter. This is a very simple monosaccharide, simple sugar that they've dissolved, evenly distributed inside of water, which would be the solvent. So in this case, glucose is a solute, water is a solvent. Let's talk briefly about some chemical bonds. Chemicals combine, they form bonding type structures, molecular structures. They are going to join together in different aspects to make different compounds, and we'll talk about a few different types of chemical bonds, as well as some of those compounds that you'll see. And again, we'll eventually get to that biochemistry area where we talk about carbohydrates, how they combine chemically to form. And you start out with some simple sugars, and you combine those monosaccharides to form disaccharides, to form polysaccharides. Eventually, you're building a complex carbohydrate. Same type of thing happens with proteins. The building blocks of proteins are amino acids. Take amino acids, you chemically combine those with a special type of chemical bond, put those together, and you're building a protein chain. And so make a note that a chemical bond is not just a physical structure, but it's stronger than that, right? It's stronger than that because it's the attractive forces of those atoms in those elements that are binding those atoms together. Usually think of chemical bonds of either forming a molecule, such as hydrogen. Usually hydrogen will bind to itself. This is what the H2 there means. Notice again, they put in there that you've got one proton. in the nucleus, one proton in that nucleus, and they have one electron that kind of just gets shared right there in the middle, and that forms a molecule of hydrogen. In chemistry, they'll call this diatomic because you got two atoms basically sharing that electron, and they come together. Once you have two or more different elements coming together, then that forms what's called a compound. And so you have a compound here of methane. You got carbon right in the middle. You got four atoms of hydrogen, and that forms that compound. Very stable compound here. I mentioned before when we looked at the periodic table and we looked at atoms in general, we said atoms are normally neutral, but what would happen if you change the electrons in there? And so if you lose an electron, that causes, if you gain or lose an electron, you form what's known as an ion. All right, and so a cation is when you have a positively charged ion. Well, how do you get an ion that's positively charged? You have to lose an electron. So if you lose an electron, remember electrons are negative. If you lose that negative electron, you get a positively charged ion. That's called a cation. If for whatever reason the atom gains an electron, and an electron is transferred to that atom, then the atom is no longer neutral. It's gained an extra electric charge, a negative charge, and so a negatively charged ion is going to be referred to as an anion. And when those come together, they're going to form a special type of chemical bond known as an ionic bond. So let's take a look at figure 2.4 from the textbook. Classic example of forming an ionic bond is you have an atom here of sodium. You have an atom here of chlorine. Individually, these are very dangerous substances. Sodium by itself is a very dangerous metal. Chlorine is a poisonous gas, but when they come together, they form that ionic bond. They basically transfer an electron from this sodium atom over to the chlorine atom, gets transferred, and they kind of get locked into place now. And that forms something known as sodium chloride, a very strong bond in this case. That's what we normally refer to as table salt. So you take sodium and chlorine gas, put those together, and you'll have sodium chloride, very safe substance, and it's something that our body needs. The strongest type of chemical bond, even stronger than the ionic bond, is known as a covalent bond. This is where electrons are shared. The first one we've already looked at was the methane example. You've got carbon here. You got four atoms of hydrogen all around that, and they're all being these electrons, these little negative portions here, are all being shared together, and so it's a very strong type of a bond there. We mentioned hydrogen, forming that hydrogen diatomic molecule. That's a covalent bond sharing there. Same thing happens with oxygen. Same thing happens with nitrogen. It'll form a diatomic covalent bond there. And so sometimes you see that atoms are just having one bond being shared, and that's called a single bond, especially like carbon can form a single bond with hydrogen. And in this case, this methane compound here forms a single bond with four hydrogens. In fact, carbon, because of its characteristics, can form up to four covalent bonds. Oxygen is here. And notice that there's two lines. Those two lines represent, each one represents a covalent bond. So this oxygen has two covalent bonds. And so that's a double bond. That's even stronger type bond there. And then you have a triple bond whenever you have three covalent bonds being shared. The last thing in this section here is another type of a bond. This is a hydrogen bond. This is a little different than those chemical bonds like ionic and covalent we were just looking at. Hydrogen bonds is what it sounds like. It's a type of a bond between hydrogen and some other atom, usually oxygen or maybe nitrogen. But a hydrogen bond is really not a chemical bond as much as it is an attraction between hydrogen and some other atom. And so we mention that here because if you kind of see this, this is water. This is a water molecule, H2O, right? H2O, two hydrogen atoms, one atom of oxygen. And because if you notice the little dotted line here, that's that hydrogen bond between hydrogen of one molecule and the oxygen of another molecule. So the hydrogen and the oxygen in the water molecule are held together by covalent bonds, but you have an additional attraction between the hydrogen of one molecule and the oxygen of another molecule. So that creates a little bit more of an attraction property that gives water some interesting and very important characteristics. One of the things it mentions here is it has surface tension, a little extra surface tension, kind of almost creates a lattice type structure with all these water molecules. It changes the density of water a little bit as well. And so, whenever water freezes, it's a little bit less dense than liquid water, which is a little different. And so, that causes water ice to float and that sort of thing. So there are some properties there. It helps it become that universal solvent to help make solutions. So it's a very important characteristic for things like water. Also find hydrogen bonds in your DNA. And so we'll talk about nucleic acids in another section. And so your nucleic acids depend on hydrogen bonding between those base pairs, A, C, T, and G. So that's just a little bit background on the first couple of sections there. I have another video that kind of goes over some of the remaining sections in chapter 2. Thanks, guys.